Let's dive a bit deeper into the concept of fluid potential and unpack its terms. Before we do though, we'll do a quick overview of some fundamental concepts that we need to be aware of. The first is this idea of energy or work, which in physics is a force times a distance. What is a force? We know a distance is just a length. A force is a mass times an acceleration. Therefore, energy has the dimensions of a mass times acceleration, which is length per time squared, times distance, length. Therefore, potential, which we described as the mechanical energy per unit mass, is going to have dimensions of energy per mass. So we'll just be getting rid of this mass term. Length squared per time squared. Excellent. And the one other thing that we said in the last video is that this concept of hydraulic head could be interchanged with potential via the relationship H times the acceleration due to Earth's gravity is equal to the potential. So I'll put this symbol up here just so we remember that. And let's see, do we get to this same answer here? Well, H is going to be length times acceleration, length per time squared. Yes, indeed, we do get to length squared per time squared. Great, that checks out. What are the various terms in potential that we need to deal with? Well, we know that there's a few different ones. One is the elevation term. It's going to be the height of an object, z or z, above some reference point times Earth's gravity. And again, we know that these units are going to give us the terms that we want here. We know that there's going to be some kinetic term, or there could be, but in general, in the subsurface, we're going to neglect it. Kinetic energy is 1/2 mv squared. If we do it per mass, we're just going to get v squared over 2. Again, we're going to typically ignore this because it's so small in the subsurface because stuff is moving so slowly. And then there's one other term here that we need to include. So this is part of the potential, this is part of the potential, and then in hydrology we're also going to include a pressure term. And we know that pressure is force per area. So a force is, again, mass times acceleration. So let's do mass times acceleration, length per time squared. Per area, length -2. What would we need to be able to convert this to get back to units of potential, length squared per time squared? Well, we need to get rid of the mass term, and we need to get rid of, let's see, some of these length terms here as well. So if we put this in the denominator, I believe we will get back to where we wanted to be. So I think yeah, this is going to give us the proper dimensions of length squared per time squared. And if we think about what this really should be here, so this part here is the pressure. This part here is the mass per volume. This is going to be the fluid density. And so this is how we relate the pressure component of fluid potential in these comparable terms where it's a length times an acceleration.